Hello everyone and welcome back to our mathematics reading group. Last time we introduced ourselves, acquainted ourselves with all of the basic kind of jargon for category theory, and today we're going to get into the real thick of it. We're going to introduce what Kashiwara and Shapira call morphisms of functors, but we're going to call them natural transformations because unless you're studying higher category theory, which we are not in this book, the idea of a morphism of functors is really not it's not that it's a bad way to think, it's just we're not going to exploit the idea that it's a morphism of functors too much. So with that said, let's just get into it and give the definition. So a natural transformation is defined in the case when you have C and D, two categories, and you have a pair of functors between them. And a natural transformation consists of the following data. We'll call our natural transformation, say, theta. And because it's a sort of de facto morphism of functors, express it like so. And this consists of the data of, for every object x in C, a map fx to gx in D, which we call theta x, satisfying, maybe putting 1 here is not necessary, I just want to say satisfying, the following diagram. Whenever we have a map f from x to y. In Emily Reel's book, Category Theory and Context, she calls the theta x the components of the natural transformation. Components. And this is sort of the right way to think about this because they're sort of the building blocks, right? These are the horizontal maps here are sort of the pieces of the natural transformation. And we put those together, and when they form these commutative diagrams, then they're called natural transformations. And natural transformations are sort of at the heart of this chapter. Almost everything in this chapter is dedicated towards giving us the tools to talk about the unit lemma. And this is sort of the most important concept for us. While we're going and making definitions, let's just make one piece of notation, which is that we can make a category of functors, usually just called the functor category, denoted by fun CD. Sort of gives you an idea of how much fun we're going to have. And the morphisms in this category are the natural transformations, because that's the morphisms of functors. Morphisms are natural transformations. And when we're interested in all of these natural transformations at once, well, we might write nat FG to denote all the natural transformations between any given two functors. This is sort of like HOM in this category. Okay, now I know that for many of you, this is ideas that you've seen before, because if you're reading Kashiwara and Shapira, you probably already know what a natural transformation is. But to my mind, no discussion of natural transformations, possibly for the first time, could be complete without the most important example. So let's give it. And I know most of you already know what I'm going to say. This is the example of a vector space and its double dual. But this really is the quintessential example. In fact, there's a sense in which all of this was invented to sort of capture what we mean when we say a vector space is naturally isomorphic to its double dual. It's the example that MacLean gives in his original paper on the subject. So let's just work this out. So let's fix a field K. Doesn't matter what it is, but if maybe you don't know so much about algebra, then maybe it's R or C or so. And let's denote by vect K the category of finite dimensional vector spaces over K. And we introduce a functor then star, which is from vector spaces to itself, finite dimensional vector spaces to itself. And what it does on objects is take v and send it to hom vk, which we know is called the double dual. And it sends morphisms, linear maps, are sent to the dual map, which we remember as an abstract map is just defined by precomposition, and as a matrix, this is just the transpose. And then, of course, we can do this twice to produce the double dual functor, which I'm not going to write out, but I'll just write star compose star. I think we all know what this means. So now what I claim is that there is a natural transformation from the identity functor, in other words, the functor on vector spaces that does nothing, to the double dual functor. And I realize my stars don't all look the same, but that's fine. So what does this look like? In order to define such a thing, we have to say how exactly the components work. So let's do that. We'll define theta v to be the map from v to v double dual, which takes a vector in v and sends it to v upper e. And this notation is for the so-called evaluation functional, or if you like, the evaluate at v map. So what this means is it accepts a vector as an argument, and it returns the functional on functionals, which eats a functional and plugs in this vector. Maybe this is a little bit of a mouthful, but I think in practice, this is something that we're all sort of familiar with from linear algebra. So what we have to do in order to check that we have this natural transformation is just redraw our diagrams and see what we've got. So on one hand, if we take the identity functor, that just leaves v alone. And for the other guy, we get v double dual. And then supposing we have any other component and a linear map, like so, what am I doing here? This should just be f. Then over here we get f double dual. Okay, so now in order to check this is a natural transformation, all we need to do is go around this diagram both ways, and we obtain the equation theta w composed with f is equal to f double dual composed with theta v, and we just need to check this. So all we're going to do is just calculate what this is in practice when you feed in any particular argument. So if we go around one way, maybe we start with v and then we first apply f. The sequence is v maps to f of v, maps to f of v upper e. And evaluating this, we just feed in some h. And of course, what you get then is f of v e h. But what's that? Well, the evaluation functional just says, take this guy, and we feed in f of v. So we get this. On the other hand, if we go the other way around the diagram, then we get v. Maybe I'll just scroll up so you can see it really quick. If we go, first we go horizontally and then vertically. Then we get v, and we get ve by applying the the evaluation functional. And then we feed in our f, which for us will be f star because it would go on the left normally, but since we can use the fact that I can remove one star and commute it past, then I get VEF star. So now we feed in another h. And all this does then is I use this, I should be very careful about my parentheses. VEF star h. So what does this give us? Well, when I feed this in, I have from the definition of VE that this is, actually, let me do it the other way. Just really, I don't want to screw up my parens. Let's do first commute the F star past the H, in which case then I get VE of H on the left, and then I get F, because I move the F to the right at the cost of the star. But now, from what I know about VE, this is just HF of V. And Of course, I just have to shuffle my parens around because function composition is associative. It doesn't matter if I do this step by step or if I do this all at once, these things are equal. So we've checked our desired natural transformation. Okay, the next thing that I want to talk about is something in Kashiwara and Shapir that I sort of got stuck on for a little bit when I first read it. It sort of took some unpacking. Not that I think there's anything wrong with what they say. There's just sort of a lot going on here. And that's the idea that natural transformations can be composed in more than one way. And they talk about the so-called horizontal and vertical compositions. And these are sort of complementary situations. So let's just take a brief moment and go through what they're saying in some detail. So first, suppose we have three categories, A, B, and C, and we have two pairs of functors. We have F1 and F2 running from A to B, and G1 and G2 running from B to C. Then we can make natural transformations, or we'll at least suppose there are natural transformations, F1 to F2, and lambda G1 to G2. And so let's just take stock for a moment about what these diagrams are telling us, or what diagrams we get from this definitions, which is that first we have from the F's, we have a diagram that looks like this, and I don't feel the need to fill in everything about this diagram. Like, I'm not going to go through and continuously remind us that we have some maps, f, x to y, blah, blah, blah. But this is what we get for our, we get families of diagrams like this for theta. And then for some different letters, maybe we'll call them A and B, we have a very similar looking diagram with the lambdas. G2 of A. And now we have to say how we compose these. So what's going on here? When I want to compose these, what I'm trying to do in this particular composition is I'm trying to first do theta and then do lambda. So I'm really trying to make sense of the idea of a composition lambda theta, like so. And so I need to say what's going on with the components. So in the case that A was actually equal to one of these, do I want to set A equal to this? How do I want to do this? I want to make a diagram that looks like this. So in order to figure this out, let's just kind of work this through piece by piece. I have G1 of F1 of X, and I'm trying to do this natural transformation all at once. So this will go then, since F1 goes to F2 and G1 goes to G2, doing them both gets me this. Aha. So we're not really changing anything here about what these A's are. It's that I'm really feeding in these functors into each other in pairs. And so all of this lives in A, since that's where X lives originally, and then we're just doing both steps at once. And the vertical arrows then are the image under G1 compose F1 of some given maps. So then up here, what's going on is we have some lambdas following thetas. And this is really this whole thing at X, is the way to think about this. Okay, and this guy is called the horizontal composition. And I know that it doesn't really look like a horizontal composition. First, I'll show you the vertical composition to sort of contrast it with, and then I'll show you why we call them this. But let me just label this as horizontal for the moment. And now, in the vertical situation, we sort of turn everything on its head, and instead of having three categories, we have three functors. So we have F, G, and H, three functors between two categories, C and D, and we still have a pair of natural transformations that we're trying to compose, except theta is now a natural transformation from F to G, and lambda is a natural transformation from G to H. And these guys we can compose by sort of concatenating the diagrams. I can draw our theta diagram. And then I can sort of immediately after this apply lambda. And this is what we call the vertical composition. Now I know that I've shown you this, now you're immediately angry with me because for a vertical composition, it looks like I've drawn these diagrams horizontally. So let me do what I said I would and explain where this notation and terminology comes from. When one is dealing with natural transformations, it's common to make diagrams that look like commutative diagrams, but are at the level of functors. So what we do is if I have my categories here, these are like objects, and then I have my pair of parallel functors instead of parallel morphisms, and maybe I'll call them F and G. And then the natural transformation is depicted like so, drawn in with a double arrow and then labeled like a morphism. And that I'm calling these things parallel and such is sort of, again, reminiscent of the idea that there's some higher categorical structure here. That's sort of, again, where all this comes from. But for us, our compositions with this notation can then be revealed pretty clearly because the horizontal composition works when you have three categories. So if instead, as in the setup over there, I called this F1 and F2, now I would have G1 and G2, and the horizontal composition comes from the overarching direction that this diagram is moving, going this way. And now it's probably pretty clear why we call this vertical, because in the other setting, what happened was we had just two categories, and we had three sort of parallel functors, which I'll really exaggerate, F, G, and H, and then we had natural transformations that are now running vertically. Just for the sake of consistency. Okay, so this is a sort of useful way of thinking, even if the notation is a little confusing. I think probably the best thing to do for the sake of notation and terminology is to sort of just avoid referencing this unless I have to. And if I need to talk about composing natural transformations, just draw the diagram and draw it at the suitable level. So I'll try to avoid saying things like horizontal and vertical. I'll try to just draw you a picture that shows you which way I'm composing them. But the thing that I really want you to take away from this is that this graphical calculus here is sort of useful conceptually. It comes with a small price, though, which is that when I'm working with diagrams of categories, I sort of need to be a little bit more careful because I need to say sort of at what level everything's happening on. I can have instances where I have isomorphisms of functors in play. And so whenever we're going to talk about diagrams at the level of categories, we're not going to talk about commutative diagrams. Instead, we're going to talk about quasi-commutative diagrams. And what this basically means is that my diagram commutes, but only up to isomorphisms of functors. These are, of course, the natural isomorphisms, the natural transformations that happen to be isomorphisms. And so to sort of keep us from getting confused, we'll just sort of make this minor distinction. Okay. Now, when we first introduced equivalences of categories, we discussed some sort of inspiration from topology, and I said at the time that there was a sort of better definition of an equivalence of categories, and I'm going to give that to you now. I'm not really sure why Kashiwara and Shapira don't give maybe the right definition first. They sort of give the working definition first, and then now we're going to prove it. But it's okay. Since we're following them, we're going to continue to do that. And now I'm going to give you the definition of an equivalence of categories that any other mathematician would tell you if you ask them what it was. So a functor from, maybe we'll call it F from C to D, is called an equivalence, well, an equivalence of categories, but an equivalence for short, when there is an inverse, not really an inverse because it's an isomorphism. So I'll call it, instead of calling it an inverse in air quotes, I'm going to call it just a quasi-inverse. And we'll call that G from D to C. And what that means is that there is a natural isomorphism from G composed with F from, well, let's see, which way does this run? G composed with F. I need to call this natural isomorphism maybe alpha, F goes C to D, and G goes backwards. So what we want is a natural isomorphism from G composed with F to the identity on C, and then similarly in the reverse direction to the identity on D. And like I said, in this situation, we call these F and G quasi-inverses. Now, what's going on with this? So this definition is sort of a generalization of an isomorphism, because when you had an isomorphism, the inverses were on the nose. So the maps alpha and beta would not just be some natural isomorphisms, but they would be literally the identity maps. And G composed with F would be actually the identity. And here, we're sort of allowing this kind of twisting to happen by some natural isomorphism. So in other words, they're not equal like they would be normally, but they're isomorphic in the sense that they're isomorphic on the level of functors. And maybe if this looks a little bit suspicious to you, then maybe a good place to get some inspiration is from topology here, at least if you've seen some topology. For example, in topology, we have the notion of a homotopy equivalence between two topological spaces. And a homotopy equivalence is a continuous map, maybe between two spaces x and y, where there's another map, G from y to x, and just sort of exactly the same way, we have G composed with F is not the identity map the way it would be for a homeomorphism, when these things would be mutually inverse. What we have are that these are homotopic to the identity on X, and F composed with G is homotopic to the identity on Y. And so just like a homotopy equivalence is a relaxed notion of equivalence in topology that sort of tells you instead of when two things are completely the same but sort of dressed up differently, it sort of tells you when they're deformable into one another. And so similarly in category theory, an equivalence of categories is not telling you when two categories are exactly the same. It's telling you when two categories are sort of deformable into one another, in a sense that we're going to continue to see more and more precise as we read through the book. The takeaway is that equivalences of categories are sort of useful for computations. And we're going to try to illustrate that with the coming lemmas, where we're going to prove that the original definition of equivalence, the sort of working definition, where two categories are equivalent if there's a fully faithful and essentially surjective functor between them, we're going to show now that that's the same as having this sort of quasi-inverse. So to do that, let's just sort of jump in, and we'll give our first lemma. We're going to have a little sequence of lemmas. Hopefully that doesn't make this video drag on too long. So lemma 1. What we have then for our lemma is a functor, which we'll call F, between two categories, C and D, and a full subcategory, which we'll call D prime. And I'm going to sort of draw a diagram as we do this. So we have C to D, and then we have this category D prime. And in the moment I'm going to include that in the diagram, but I haven't yet. And the important thing about D prime is that we're going to have the property that for every x in C, for every x in C, there is an isomorphism, some isomorphism, from f of x to some y in D prime. So again, F doesn't really map onto D prime. F maps onto, but F does map onto things that are isomorphic to D prime. And in this case, we claim that denoting, actually before I say that, like I said, let me put this into the diagram. Then we denote by I the inclusion as a functor from D prime to D. And in this case, then there is a unique functor which we'll call F0. And F0 will have a natural isomorphism, which we'll call maybe theta, from F to I composed with F0. Oh, I'm so sorry. I didn't tell you. Okay, well, maybe it's obvious from what I've said, but I shouldn't be so sloppy. F0 has to run C to D prime, like so. So in other words, I can sort of construct a functor out of F, which actually maps onto all of these target isomorphic objects, so that when I map forward my I, then I have a natural isomorphism. And as a last remark, I claim F0, I didn't, maybe a better way of saying this is I didn't say what the uniqueness means. Unique up to a unique isomorphism. Okay, so let's see how we prove this. It's not tremendously difficult. We just sort of work in a few steps. And step one is sort of, as for all of these constructions involving large categories, where we need to make a lot of choices about what these isomorphic objects are, is we need the axiom of choice. So first thing we do is, by the axiom of choice, we actually choose a representative for all of the target objects. So for every x in C, we're going to go ahead and identify a y in D prime and an isomorphism, because there could be more than one, from fx to y. Okay, once we've made all these choices, we're going to define, just take this construction as our definition of f0. So we declare that f0 of x should be y. And we have to now say what the morphisms are. So to say what f0 does to morphisms, then we take any morphism f, maybe from x, and I'm already used y, so I'll use x prime. Maybe this is any morphism. Then we define f0 of f to be the map f0 of x to f0 of x prime, which is defined by the following composition. I go from f0 of x to maybe, I didn't label what these maps are. So let's call these isomorphisms phi x. So we go from f0x by phi x back to ordinary f of x. And now I can apply f of f. What am I doing? And now I have, this gets me over to f of x prime because that's what f does. And now I apply phi of x prime inverse. Oh geez, I'm really doing bad here. This should go up here. And that gets me to f0 of x prime. Okay, so this is a complicated looking definition of f0 of f. It's this whole big composition. So we need to check that this is actually a functor. So let's do that. Not so hard. We have a big diagram where we start with f of x, and let's just record what's happening up in the big category. And really what we're checking here is that this sort of distributes over morphisms, because that's really the non-trivial thing to check here. So this is f of f, and maybe we have some other map. This will be f of g. And then now down in the small category, we have f0 of x over here, and we have phi of x. And remember that this is our object y here. And we have f0 of f over here. And this will be our guy y prime, which we remember is f of x prime, or it should be f0 of x prime, phi y, and f0 of g, I've been sort of sloppy about where I'm putting these, but it's fine. We'll call this one y prime, and this will be, I should get my notation right. This should be phi of x prime, and this will be phi of x double prime. Okay, now we've got that right. We need to actually check that this diagram is commutative. So what we have to do is remember this definition here, as where these f0s are these compositions, where we do phi x. So maybe let me just write this formula here just to be clear. Put it in one place. First we do, well, I guess we should go in the reverse order. So last we do phi of x prime inverse. In the middle we have f of f. And then over here we have phi of x. So if I was going to compose these end to end, then f0 of gf would be phi of x double prime inverse composed with f of gf composed with phi of x. And since f is a functor, it would distribute. And that represents sort of going around the top path of this. And what we get then is we can insert in here the missing inverse phi x prime and phi x prime inverse, just right in the middle. And if you've done any group theory or so, you've probably seen arguments that look like this a million times. This corresponds to just going up and down that one arrow there. And this is, of course, f0 of g composed with f0 of f. So we've done it. Okay, so now what we have to do is see that this assignment is a natural isomorphism. But this is sort of clear, because the way we constructed this guy is by using the chosen isomorphisms, the phi x's. And so if we had, and finally, so if we had any different choice of isomorphisms, maybe we call those some theta primes or so, then all we would have to do is just choose the isomorphism that relates the theta and the theta primes, which undoes one of them and redoes the first. So maybe I'll just call this an upshot. Uniqueness is easy. Undo one isomorphism, then do the other. And again, the sort of usual group theoretic arguments are going to tell us that these things are equal. Okay, so why are we proving this lemma? This lemma motivates the following very important definition. Definition. So C will be a category. And we'll call a skeleton of C is a full subcategory of a full subcategory, maybe I'll give it a name, D of C, containing a representative of every isomorphism class. And, oh, this is important, no two distinct objects of D are isomorphic. So in other words, one and only one representative. Okay. And so the useful thing about this definition is that skeleta, maybe I'll call this an observation, skeleta are trivially equivalent to the categories that they are skeletons of. Sort of motivates the name. We're thinking of this as picking out just the bones, so to speak, of the category. And if this is not completely clear, then maybe just sort of scroll back up and spend some time and think with this, because this is sort of should really be obvious to you guys. So lemma 2 is that skeleta always exist. And this is, again, a very simple argument using the axiom of choice. All we have to do is choose isomorphism representatives, as before. And then we take these choices of objects to be our skeleton. And then for the morphisms, we just take all of them. So this constructs the category. All we have to do now is see that this is actually meets all the requirements of the definition. And this is not very difficult, but we'll do it. What you do is you take the embedding, which we'll call I, from D into C, and we just apply this previous lemma to the identity functor. And what this does is produce for us our functor F0, C to D, and then I composed with F0, I composed with F0 is isomorphic to the identity. And this gives us the following very simple calculation. We have I composed with F0 composed with I. This is, of course, just I of F0 composed with I. But this is isomorphic to the identity on C composed with I, which is also the same thing as I composed with the identity on D. And I is fully faithful by definition, which I'll just abbreviate. And so it follows that F0 composed with I is naturally isomorphic to the identity from this calculation. Identity on D. Okay, now we're ready for the last result of the video. And I'm sorry, this video is approaching 40 minutes already, but here is the proposition. A functor is an equivalence of categories if and only if f is fully faithful and essentially surjective. Okay, so to do this, notice first that, actually, let me scroll down before I start talking proof. So if f is an equivalence of categories, it follows immediately from the definitions that f is full and faithful. Maybe I should write this down. If f is an equivalence, implies f is fully faithful. And the way you see this is we know that f composed with g is naturally isomorphic to the identity. And so that natural isomorphism gives us the requisite bijection on Homs that it takes to be fully faithful. And then we need to see that f is essentially surjective, but this is clear. And that's because f is essentially surjective when the identity map is surjective, sort of trivially, and our functor applies an isomorphism, which lands us into the desired isomorphism class. Maybe saying that a little bit slower. Maybe this isn't completely clear, and I should be clear. F is essentially surjective because we have this relation to the identity map, which is trivially surjective. And our natural isomorphism, while it doesn't, while our functor here doesn't land us onto every single possible object, it lands us onto every isomorphism class. Which is sort of all it takes to be essentially surjective. Okay, so that handles the forward direction. Now we have to do the backwards direction, and this is a pinch harder, but not so bad. Let's maybe label this forwards. Come on, go back up, please. Forwards. Now let's do backwards. And for this, we use the lemmas. So first, by lemma number 2, we pick a skeleton. And we'll call that skeleton CS, just to sort of make it clear what's going on. And we pick an embedding I from CS into C. And what we do is then choose a quasi-inverse. And this quasi-inverse will denote by Kc. All right, the quasi-inverse to the embedding. Sorry. And now we'll have to have ourselves a think about D, and we do the same thing. We need a, should I call this J, or do I want to label this IC? Let's call this IC. And now let's choose a skeleton of D, and a quasi-inverse. Okay, so we make all our choices. Now let's consider what happens with the composition where we're just going to sort of go around a commutative box, and I'll draw you a diagram to show what's going on in a sec. And then F, and then KD. So what's going on here? We have C and D, and our functor F. And then we have CS, and here we have IC, and here we have KC, and here we have DS with ID and KD, and our composition goes from CS up to C, across and down. So we end up with a picture that looks like this. And this composition is actually an isomorphism. And this is just because skeleta are equivalent to their big categories. So the composition has to be an equivalence. However, every object only appears in the skeleton once. So the definition of skeleta, well, when I say once, I should say each isomorphism class only has one representative. So the definition of skeleta upgrades to isomorphism. Okay, so now what that means is we can construct an inverse to this map, which maybe we'll call, let's pick a color because this diagram's getting a little cluttered. So let's take this inverse guy. And how should we construct this? Let's just call it K. And such an inverse exists on the level of skeleta because of what we just proved. But we can also form the reverse composition, right? We can define, maybe you'll call it G, will be IC composed with K, composed with KD. I kind of regret overloading this letter K here, but what this does here is it starts us up in D, we go down to the skeleton, use the inverse we just constructed, and then go back up to C. So now that we've got this, we have a map G, which is going in reverse to F. And so now let's think about what happens when we look at GF of X. So this is a long composition, but we can sort of see what it does graphically here. We take our object X, and we map it over to D by F. Then we descend to its isomorphism class in the skeleton. We send this back over to C skeleton using the isomorphism K defined below, and then map that back up into C using the inclusion. So basically what this map GF does is, up to this business of these quasi-inverses here, is it sends us around this loop. So we just start in C, and we cycle all the way around. Now, the upshot to this is that this is the same isomorphism class of X, because we never left the isomorphism class. We applied either isomorphisms directly or quasi-isomorphisms. or sorry, what am I saying? We applied equivalences. Excuse me. We applied equivalences and inverses everywhere. So this gets us into the same isomorphism class. And similarly, for FGY. Completely analogously. So then we can use these to construct the natural isomorphisms that it takes to prove this. And so we've really done here is we've written down a quasi-inverse to F. Which is what we needed to do. So this implies F is an equivalence of categories. Okay, I think this has gone on more than long enough. Next time, we'll introduce the most basic notions that we need towards the unidilemma. We'll start talking about, in fact, I think we'll actually prove the unidilemma next time. Although we definitely won't have time to talk about all of the great things that one gets out of the unidilemma next time. We'll get started talking about pre-Sheaves and representability. All right, looking forward to seeing all of you then.